Hey, good morning or good afternoon. Dr. Patton, live from the Fortress of Solitude here at the University of Tennessee, Chattanooga. Hope you're all doing well. This lecture will be in conjunction with the PowerPoint that I have posted for Wednesday's lecture. And just a few announcements before we start. There are some deadlines. Assignment 5 and 6 are coming up on sapling. Those are going to be on April 10th and 16th, respectively. Friday, April 17th, you'll have exam 3 that'll cover EDTA titrations, UV vis absorbance, electrochemistry. And today, we're starting our final topic of the course, chromatography. But before we get into chromatography, we need to discuss separations. So these topics regarding separations are in Chapter 7 and 12 in the online textbook from Harvey, and Chapter 22 in Harris discusses analytical separations. Now, when we think about analytical chemistry and what we do, we make measurements of a species, a particular analyte, and we get some information from the measurements that we make, whether they be an absorbance measurement, whether we're doing a titration, whether we're doing some electrochemistry. But the issue is sometimes our analyte is in a complex mixture of other species. These species might interfere with the signal that we want to measure, that we're trying to get information about our analyte. They might be, if we're doing organic chemistry, analytical chemists might help the organic chemist by identifying if a product is pure. And sometimes we get some byproducts that we don't want. So sometimes we have to do some separations to get out what we want. So the first thing we're going to discuss about in separations are solvent extractions. So let's just think about a solvent extraction. Solvent extraction, and let's define a few terms, because again, we have a lot of different language in chemistry that some people need to understand some terms. Now, what an extraction is, let's look at this word right here, extraction. Extraction. So an extraction is defined as the transfer of a solute from one phase to another. So we're going to transfer our solute. And remember, our solute is our analyte. Transfer our solute from one phase to another. So let's think about this phase term I'm using here. Now, when I'm saying phase, what we're going to do is we're going to use and encourage this transfer or extraction movement of our analyte between two immiscible phases. When I say immiscible, what I'm going to think about are two liquids, and that's our simplest discussion here, two liquids that don't mix together. Think about oil and water as an example. You take some oil, you mix it with water, you shake it up, but they end up separating. And that's because they have different intermolecular forces that cause them to not want to interact together. Water is polar. Organic solvents are nonpolar. Polar and nonpolar liquids don't mix together too well. And that's why we see oil slicks on top of water. It really depends upon the density of how they separate one on top of the other. But what we're really going to focus on is something we probably remember from earlier science or chemistry classes, and that's like dissolves like. And that's essentially what we're focusing on here. We're going to try to encourage our analyte to move into one of these immiscible phases, depending upon whether our analyte likes nonpolar environments or polar environments, such as an aqueous environment. So we're going to look at a solvent extraction involving water as our polar solvent and an organic solvent. If you haven't taken organic chemistry, organic compounds are going to be compounds that have usually long chains of carbon and a lot of hydrogen, and they're not very polar. They're very nonpolar. And as we said, this would be a really good example of what we see when we have an oil slick. Oils, waters don't really mix that well. So what we're going to do is we're going to take our two immiscible phases that we've been discussing. So remember, our immiscible phases are going to be water and an organic solvent. And we're going to put them into a glass device known as a separatory funnel. So let's look at what a separatory funnel. You may have remembered this if you had an organic chemistry class of what a separatory, or sometimes we'll just say a sep funnel. So a separatory funnel, do my best to draw it. I have a few images on my PowerPoint. Separatory funnel. It has a little stopper on the top, and it's sort of shaped like that, and it usually is fixed with a stopcock on it. And then up here is a removable stopper that we would have on the very top. So if we put in our two immiscible phases, water and an organic solvent, and we allow them to partition or move away from each other, we're going to get an interface between the two. And we're going to look at a situation in which our organic solvent sits on top, and we're going to look at a situation in which our organic solvent is less dense than our aqueous phase, or our aqueous, which is more dense and sits on the bottom. So good picture there I have. I actually have a color picture of something I stole from the internet. Don't steal from the internet. I didn't steal, I borrowed it. So we're going to look at the term partitioning. Partitioning. So partition. Partitioning is going to be the movement. That's another term that we use, partition. Partition is the movement from one phase to another. And our analyte, depending upon whether our analyte, our solute, is more polar or more nonpolar, it's going to have a favorable partitioning or movement either into the aqueous or into the organic phase. And what we're trying to do is remove that analyte from interfering species in the phase that it originally is in. And hopefully, if we can move it from one phase to another, we can isolate it, and we're going to separate it from interfering species or from anything that we want or don't want from an organic chemical reaction. So what we measure in terms of the process that's occurring is an equilibrium. So let's look at what I have in my next image if you have the PowerPoint. And we're looking at this environment using a different image rather than our separatory funnel. What we're going to encourage here, once again, is the movement or partitioning of our analyte between two immiscible phases. And we use the double-sided arrow because this is an equilibrium process. And if this is our aqueous phase down here, and this is our organic phase, and our species, we'll just call it S, our analyte that we're focusing on. Square brackets represent the concentration, and we'll give this a subscript 1, and we'll just call this subscript 2, just so we can identify these. This is going to be the concentration of our solute, our analyte, in phase 1, our aqueous phase. And this is going to be the concentration of our analyte in phase 2. And again, the double-sided arrow informs us that there's an equilibrium occurring, and we can define this equilibrium constant K. And again, we're looking at this directionally as going from the aqueous phase into the organic. So this is going to be the ratio of the concentration of our analyte, S, between these two phases. This is the concentration of S in the organic phase versus the concentration of S in the aqueous phase. And this equilibrium constant has a name to it. It's called the partition coefficient. That's a K in this respect. It's capital K. Make sure you know it's capital K, because later in this discussion on chromatography, we're going to be using a lowercase k. So what we're going to focus on now is, if we know a little bit about the equilibrium that's occurring, we can understand a little bit about the efficiency of an extraction strategy. And the way we can define the efficiency of an extraction strategy is looking at the fraction of the species that remains in one of the phases. And what we're going to look at is we're going to look at the fractional amount of our analyte that remains in the aqueous phase. So if our goal is to move it into the organic phase, we would prefer to see a smaller fraction remaining in the original aqueous phase. And to understand extraction efficiency, we define the fraction that remains in the original phase, Q. We'll just put a 1 by it, Q1. As being related to the volume that was originally in phase 1 and the aqueous phase, V1 divided by V1 plus K, our partition coefficient, times the volume in V2. So let's define all these terms so we know what we're talking about. Q is the fraction of our analyte S in phase 1. And in this particular arrangement, it'll be in the aqueous phase. V1 is going to be the volume of phase 1 in milliliters. V2 is the volume of phase 2. And in this case, what we're doing is we're taking a volume of an organic solvent and we're adding it to our aqueous phase. We're shaking these up in our SEP funnel. We're allowing them to separate. And what we're hoping is that based upon the equilibrium that occurs during the partitioning, our analyte will be moving into the organic phase, and we're going to be able to calculate the fraction of our analyte that remains in the aqueous phase. And that's going to tell us a little bit about how efficient our process is. And what we're going to show in this exercise that we're going to be doing in a few minutes is that this would be related to the fraction that remains in one single extraction that we do. But our efficiency can be improved. We can improve on our efficiency by doing single smaller extractions with smaller volumes multiple times. And when we do that, we're going to show that we can improve on the efficiency by doing multiple extractions. So this is Q remaining in our first phase. N is going to represent the number of extractions that we do. And again, it's related to the same equation. But we raise it to the power based upon how many extractions that we're going to be able to do. So let's envision why this relationship is true. We go in, we have a fraction of our sample that remains in the aqueous phase. We add fresh organic phase, and then we're going to shake it up again. And what's going to happen is a fraction of the fraction that was remaining is going to be the result from the second extraction that we're doing. And so when we add up our Q's, we can think of this as being Q1 times the Q2 of our second extraction. And as we keep going through, we end up with a power relationship to these percentages that we have remaining at the end of an extraction. So I'm going to go over an example that I have listed on today's PowerPoint so we can evaluate the efficiency of multiple extractions versus a single extraction. Let's leave this information up here and let's work on our problem. So we're going to look at an example problem. So our problem is looking at a solute. We'll call it the solute A. Solute A has a partition coefficient K of 8.5. And we're going to look at it just like we've been describing. What this tells us is that K is 8.5. And remember, this is the ratio of our solute moving into the second phase over the first phase. And that tells us that our solute prefers to be in the second phase since K is greater than 1. And we're putting this in an organic layer, an organic solvent of toluene, and we're going to be using that for our extraction. Now, what we're going to look at is we want to calculate. We're going to calculate the percentage of A that remains in the water phase in our aqueous environment and we're going to look at the efficiency of doing either A, one extraction, with 50 milliliters of toluene, or B, 5 extractions with 10 milliliters of toluene for each. So toluene is our organic phase, And if you recognize the total volume of toluene will be the same after the 5 extractions, but the multiple extractions is going to give us an overall better fraction of our analyte that's going into our organic phase in comparison to the aqueous phase. And in this problem, we're going to say that our solute A is originally in 100 milliliters of water. So let's just draw a little diagram so we know what we're doing. A little picture helps. Pictures are really worth a lot. So here's our separatory funnel. Not the best. Not really an artist. We have 100 milliliters of water with our solute A in there. And what we're going to do for our first experiment is we're simply going to add 50 milliliters of toluene. We're going to shake it up, and A is going to favorably distribute into the toluene organic phase. And it has a partition coefficient of 8.5 that tells us that it preferentially wants to go into the toluene phase. Shake it up, let it equilibrate. We're going to drain off the water, and then we're going to see what fraction of our solute remained in the water. And that'll tell us a little bit about the efficiency. And we're going to use equation 1 up here, this first equation, because all we're doing is a single extraction. And what we're going to calculate is the fraction that remains in water, and we'll convert that into a percentage. So let's look at the numbers that we have available to us. V1, well, that's the 100 milliliters of water. V1, 100 milliliters in the denominator. K is 8.5. V2, well, that's the 50 milliliters of toluene that we're using for the extraction. This is going to tell us a little bit about how much of our analyte is still in the aqueous phase. How much of it did we actually get out? Well, we want Q to be small because we want more of it to be in the organic phase. So what's Q after one extraction using 50 milliliters? The fraction is 0.19, or if we convert that into a percentage, 19% of A is still in the water. Okay, let's show that it's better to do 5 small extractions. In other words, we're going to go through this experiment again, and we're going to use 10 milliliters of toluene. Shake it up, let it equilibrate, and we're probably gonna have to drain the water portion off and keep this portion of toluene, and then take this sample that still has some toluene or analyte in the aqueous phase, add a fresh 10 milliliters of toluene, shake it up, let it equilibrate, do it again to the aqueous phase 3 more times, and then when we're all done, we'll combine all of the phases that have toluene and our analyte. And what we want to do is look at what fraction of our analyte will be in the final aqueous phase after we do this exercise 5 times. So this is for, we're going to just raise this to the power of 5. And if we put all of our numbers in here, it's 100 milliliters. That's the volume of our water. 100 milliliters is in the denominator. K is still 8.5. V2 is now 10 milliliters. And we would take that argument that we get in those parentheses and we would raise it to the power of 5. And what we would get is that the fraction of our analyte in the aqueous phase, 0.046, or this would tell us that only 4.6 of A is still in the aqueous phase. A single extraction with 50 milliliters, 19% of our analyte is still in the water phase. If we conduct 5 extractions with small volumes of our organic phase, we end up with a 4.6% of our analyte still in the water. So this is a more efficient way to conduct an extraction using smaller volumes of our extracting phase, in this case, our toluene. So that discusses, we just, good discussion on liquid extractions. The problems with liquid extractions, they do suffer. They do suffer from 2 limitations. First of all, notice this is a better way to conduct our extraction, doing multiple small steps. Well, guess what? That becomes tedious and time-consuming. If this is what we would need to do to get a better separation, that's going to cost a lot of time. And if we're working in industry, time is money. And if you're in grad school, time is your life. So it's up to you. So that's one problem with doing extractions. They take a lot of time and they're pretty tedious. Another problem, if you recognize, even after 5 extractions, we still have 4.6% of our analyte still in the aqueous phase. Might have to go on and on and on. And another issue is that some of the interfering species or our byproducts that we don't want, well, they might be extracted also. So there might be an incomplete separation of our analyte from stuff that we don't want. So that's not good. So what we do for better efficiency, better separation methods, we use chromatography. And chromatography operates on the same principles that an extraction operates on. That's why we learn about it. Chromatography is more effective than a liquid extraction for most processes, and it uses the same principles. And what we're going to discuss more on Friday in our lecture is a comparison of several different types of chromatographic methods. So let's think about chromatography as a teaser for Friday's lecture, so you all come back. Chromatography. Now, chromatography, it's a nice word. Color writing. And that's because the guy that invented this, Mikhail Tswett, Russian chemist, biochemist. Tswett, T-S-W-E-T-T. I believe that's how you spell his name. Now, Dr. Tswett, he was working on his second PhD. I just learned that today. He took plant pigments and he was able to separate them based upon differences in their solubility in different types of phases, just like we did in a liquid-liquid extraction. But what we're going to do in chromatography, instead of having two liquid phases, we're going to have one we call a stationary phase. And as the name implies, it's going to be a supported phase that doesn't move. It's stationary. Now, the stationary phase are typically going to be a solid or a liquid. And it's going to be exposed to or have flow over it a mobile phase. Mobile phase is mobile. It's going mobile phase. It can move. And our mobile phase is typically going to be a liquid or a gas. And what we're going to do is we're going to flow our mobile phase over our stationary phase. And just like we did before, in terms of like dissolves like, our analyte is either going to want to spend more time in the moving mobile phase or more time on the stationary phase that doesn't move. And that's going to encourage its separation from another species, which could be an interfering species or a byproduct that we don't want, that's going to interact with either the mobile phase or stationary phase differently. And we're going to encourage a separation based upon these interactions, their differences between the two phases. And we're going to focus on two types of chromatography in our lecture on Friday. One that you may be familiar with, we'll briefly just touch on TLC. And this is the TLC that means thin layer chromatography. And column chromatography. And this is the topic we'll be spending most of our time on at the end of this semester, column chromatography. TLC, thin layer chromatography. If any of you have had organic chemistry, you may have some experience with thin layer chromatography. Now, what we do with thin layer chromatography, we'll get into column chromatography in greater detail. Thin layer chromatography uses as a stationary phase, in most cases, in many cases, I won't say most, in a lot of cases, a silica support, SiO2. This is the solid or stationary phase for TLC, thin layer chromatography. And normally what we're going to use for our mobile phase in TLC normally these are going to be a nonpolar organic solvent. This is nonpolar. So for this to work effectively, if this is nonpolar, our stationary phase, which is a silica gel, is going to be polar. So what we do in using thin layer chromatography is we use a glass slide that has the silica sort of like painted on there. It's a gel. And what the surface has on it, if we look at it from a side point of view, it has silica groups that have exposed oxygens and hydroxide groups off the silica. So this gives us a fairly polar surface in which analyte or species that are polar will interact with more. And they also will experience hydrogen bonding. So if we have two components that we would spot on here, I'll use different colors. We have component A, and we have component B. And we spot them on our plate. So typically we use a pencil and we mark a small line where we spot these two samples. And this would be our plate. We'll just put it like that. And we know that the surface of the plate has these exposed selenol groups. We would have these sitting in a chamber where our two components are below an organic solvent that's nonpolar. And by capillary action, the organic solvent moves towards the top of the plate, and our two species will interact differently with our organic solvent, which is our mobile phase, as our species A and B will either want to spend more time in the non-polar mobile phase, or they'll interact strongly with the polar solid phase. And so if we'll just assume, let's just think, if A is more polar than B, A will move slowly up the column or up the plate, and we might see a spot there. B, which may be a compound that's less polar, would spend more time in the mobile phase, and B would move further along that plate. And so this essentially discusses about how thin layer chromatography works. Understanding about thin layer chromatography and liquid-liquid extractions are going to be really helpful when we start to discuss chromatography on Friday. So we'll end with this, and we'll get into some more details about thin layer chromatography and a lot of details of column chromatography when everybody shows up on Friday. Good luck. Have a nice afternoon, and take care of yourself. Didn't save it. Didn't save it, did it? No. Oh, there we go. End.